Greetings to all and welcome to this lecture. We are in Module 1, Review of Semiconductor Fundamentals, lecture number 4, PN junction part 1. In previous lecture, we have discussed about the basics of semiconductor and we concluded that we do have two types of semiconductor, that is N-type and P-type. And we do have two types of charge carrier, that is N, which means electrons, and P, which means holes. So let's build a simplest semiconductor device, that is PN junction. It means we will form a junction between an N-type semiconductor and a P-type semiconductor. Strictly speaking, it is not like gluing the two types of materials together. You need to have a proper diffusion and you need to create a junction in a same substrate. So this is N-type and this is P-type, forms a PN junction. We will analyze this PN junction under equilibrium case and forward bias condition in this lecture. These are the learning outcomes of this lecture, which helps you to understand the PN junction theory under equilibrium, what is built-in potential, and how the energy band diagram can be plotted for PN junction. This lecture also helps you how to get the diode equation or diode current equation by solving different approximations. Let's do a quick recap. In last lecture, we have discussed about the transport of charge carrier. It means N and P. So we said that we do have two types of transports. One is drift and another is diffusion. So we concluded that when you applied a potential along a semiconductor bar, then this potential changes the velocity of the charge carrier, and hence equivalent you can move the charge carrier from one position to another position, and hence it gives rise to a current. We have also concluded that in general the drift and diffusion can be explained by a net flux which moves in the semiconductor from one position to another position, either by applying voltage or due to concentration gradient. So this can be written as P into V divided by 2, where we said that this is hole concentration and this is the velocity of the charge carrier. If the electron concentration or the hole concentration is not same in the material, but the velocity is same, meaning you are not applying any external bias, then also there will be a current. This gives rise to a diffusion current. And if the concentration is uniform but you are applying voltage and hence the velocity of the charge carrier is different, then this is called as drift. We have also seen that under equilibrium condition the net current out of semiconductor is 0. It means even if non-uniformly doped semiconductor has been taken, the diffusion exists but it will be counterbalanced by the drift, and hence the net current will be 0. We have also seen that how the Fermi level position varies in terms of drift and diffusion. So let's use the previous analysis to design a first semiconductor device which is nothing but a PN junction. So here N-type material and P-type material has been taken and they formed a junction. This is known as metallurgical junction, where this N region and P region meets. So when you joined N-type and P-type, then what will happen? Because of high concentration of electron at N side, it will diffuse towards P side, and similarly, so electron generally represented by the dots and hole represented by the bubbles. So due to the heavy concentration or high concentration of holes at the P side, it will diffuse towards the N side, and there will be a huge diffusion current flows into it, right? So in this condition we are assuming that N plus is heavily doped. So plus stands for heavily doped and P region is lightly doped or moderately doped. These two caps are formed by metal to form a ohmic contact in this junction. In a very first case, we are assuming that these two contacts are shorted to each other and hence no potential is been applied here. Let's analyze what will happen when you short the external wires of N and P. So the moment you connect N and P, they forms a junction at this metallurgical junction. So due to higher concentration of holes in the P side, they will diffuse in this side. Similarly, higher concentration of electrons from N side to P side, it will diffuse from this side to this side. If the holes are diffusing in this direction, ultimately what will happen, there will be a diffusion current. So I diffusion due to hole, which exists from left hand side to right hand side. Similarly, if the electrons are diffusing from higher concentration to lower concentration, then there will be a current opposite to the direction of electron flow, and hence the direction of diffusion current due to electron is in this direction. So ultimately you will get a net current of diffusion from left to right. But now what will happen, the moment the hole will leave this side, it will leave a immobile ions. This immobile ions is nothing but acceptor ions. Then when the flow of holes started from this side to this side, more immobile ions will be uncovered. Similarly, more number of donor atoms will be uncovered at the N side, and hence this form a depletion region. Depletion region means a void region where we consider that there is no electrons and holes present into it. This approximation is known as depletion approximation. We will develop our theory based on the depletion approximation, considering that there is no mobile charge carriers in the depletion region. Practically, there are few mobile carriers exist into the depletion region which supports the current. Now, if there are immobile ions separated by some distance, then there will exist an electric field in this direction. That electric field is this. Because of this electric field, ultimately the flow of electrons and holes from their respective regions will be stopped, and hence there will be an equilibrium established. Meaning, if there is a positive charge, this positive charge repel the holes and it will say, no, you cannot come now. So the flow of holes will get stopped. If the flow of hole gets stopped, similarly, because of this negative ions, the electron get repelled in this direction, and hence the flow of electrons will stop. So there will be a drift current which is in this direction. So hole is actually going this direction, so I drift of hole in this direction, and electrons are going back because of this supply or this internal electric field. So there will be I drift of electron which is in this direction. If you see carefully, the diffusion force on electrons and the drift force on the electrons is exactly counterbalanced to each other. So equilibrium established, and you can say if the outer leads are shorted or they are open, there is no current. So I net will be 0. So there will be a charge balance happen which says that the diffusion of holes and electrons is exactly counterbalanced by the drift exist into this. This region is known as space charge region or depletion region. Let us consider our example where we said that we do have PN junction where N is heavily doped and P is lightly doped. So let us consider the doping concentration of N is 10 to the power of 17 per centimeter cube, and this is, let us say, 10 to the power of 15 per centimeter cube. Now, can I show this concentration of holes and electron in a scale? So if I really want to show the concentrations of holes and electrons, then I need to choose log scale. Why? Because we have discussed already that in the semiconductor, the product of electron and hole is nothing but what? Ni square, where the order of Ni is approximately 10 to the power of 10. It means if there are 10 to the power of 17 electrons exist in the N plus side, then 10 to the power of 3 per centimeter cube holes will exist. Similarly, if the holes at the P side is 10 to the power of 15 per centimeter cube, then Ni square by P will give you the electron concentration. Now if I want to show the change of these order in a same scale, I need to choose log scale. Let us consider this is 10 to the power of 17, 16, 15. So here this is the whole concentration at p side. Similarly this is 17, so this is electron concentration at n side. Now if there are holes at the p side, there are electrons, which is, let's say, 10 to the power of 5 electrons at p side, and similarly 10 to the power of 3 holes at n side. Now if you see, we do have same symbols to show p, n, p, n. So to avoid confusion, we need to add subscript. The subscript says the holes belong to which region. So p stands for hole from p region, n stands for electron from n region, pn hole from n region, and np electron from p region. Now ultimately what is happening, the concentration from higher concentration to lower concentration, it will go. This causes the diffusion. Similarly, the electron will go from higher concentration to lower concentration. Keep in mind that every point, if you calculate the product of n and p, it will be Ni square. This point where it exactly meets is called an intrinsic point, and due to charge balance, it always lies in the lightly doped side. So there is a depletion region where this is positive immobile ions and there are negative immobile ions, and this is what is called depletion region. Now let me ask one question: can this connecting line have a discontinuity? The answer is no, because this line shows what? The gradient of p over x, if this is the x direction. If this is discontinuous, it means the gradient of dp by dx is infinite, and which gives rise to the diffusion current to be infinite, q into dp into dp by dx, which is not possible, and hence this should be continuous. Correct? So we start our analysis to calculate what is the charge available into this semiconductor, what is the charge available into this depletion region, and how does the electric field and the built-in potential exist, because the separation of this positive charge and negative charge creates a built-in potential here, which is denoted by phi bi. So under zero bias condition, we will analyze the p-n junction to find out potential barrier. Let us understand the potential barrier in terms of band diagram. So I am redrawing here the band diagram of n side and p side. In separate, if the two semiconductors are separate, then n type band diagram can be plotted like this. This is EC, this is Fermi level, intrinsic level, and EV. As under zero bias condition, there is no current flows, and hence the Fermi level will be constant. So this is Fermi level, and we need to build the valence band and conduction band accordingly at p side, considering both p side and n side are made by silicon. So band gap will not change, and ultimately there will be a continuity in EC and EV. So that is what it is here. Now if you see, the intrinsic Fermi level should also be continuous. We can extract few more information from here. If you see carefully at this side, the slope of EC, which is nothing but 1 over q dEc divided by dx, is nothing but 0. It means we can assume that the electric field beyond this depletion region is 0. So this region is called as neutral region of p-n junction. Similarly, this region is neutral region. The bending exists only in the depletion region, and hence the field exists from n side to p side. So there will be a field exist into it. Now I need to calculate what is this potential barrier. It means if an electron hop from the valence band to conduction band at n side, it will face a potential barrier and it cannot go to the p side. So what is this potential barrier? Height. This is nothing but q times of phi bi. As we are plotting the energy in electron volt, so we need to multiply q in phi bi. If you see carefully, this phi bi can be calculated as this difference plus this difference. This difference is nothing but E f minus E fi by kT, and this difference is nothing but EFI minus EF by kT. Again, to avoid confusion between the Fermi levels of different regions, we are adding a subscript EFP and EFN. So this become EFN and this become EFP. So ultimately the total sum of these potentials will give you the potential barrier or the built-in potential, right? So ultimately you can rewrite these equation by your basic understanding which we discussed in previous analysis, that n naught can be written as ni e to the power of, now we need to choose a positive exponent, so EFN minus EFI by kT. Similarly, P naught can be written as ni e to the power of EFI minus EFP divided by kT. Correct? If I want this, so this is equation number 1, equation number 2. If I want this, I will take log of equation number 1. It will give me EFN minus EFI divided by kT is equals to log of n naught by ni. Similarly, this will give me EFI minus EFP divided by kT is equals to log of P naught by ni. Now if I want a potential barrier, I need to add these two quantities, one quantity and another quantity. This will give me the total height. So ultimately q times of phi bi is equals to, so there will be a kT terms come into picture, kT log of n naught by ni plus kT log of P naught by ni. Now if it is an n-type semiconductor, n naught is nothing but Nd, and if it is a p-type semiconductor, P naught is nothing but Na, the acceptor doping, and hence we can rewrite q into phi bi is equals to kT log of Na Nd by Ni square, where if you divide by q, this kT over q is nothing but phi t. So you can rewrite as phi t log of Na Nd by Ni square. So this is the built-in potential which exists in p-n junction. Interestingly, if you remove this connection, then also the internal structure or internal built-in potential will not destroyed. It will exist even in zero bias condition, or this is called under equilibrium condition. We can derive an interesting junction law by using this equation. So the built-in potential phi bi is nothing but phi t log of Na Nd by Ni square, where Na and Nd are the doping concentration of p side and n side. Now suppose you know the whole concentration at p side, Pp, but you want to calculate what is the whole concentration at n side, Pn, right? Can I use this equation to calculate the whole concentration at other side if I know the whole concentration of one side? So you can simply do this phi t log of Na. Na is nothing but the whole concentration at Pp or whole concentration at P side, this Ni square by Nd can be written as Ni square by Nd. This is nothing but the minority carrier concentration or whole concentration at N side. So, this can be written as phi t log of Pp divided by Pn, which is nothing but phi b. Meaning, across the junction, if you know one kind of doping, which is let us say Pp, and you want to calculate the other side of the doping, but you know the built-in potential between this junction phi bi, so you can simply calculate the doping of other side, which can be as Pp is equals to Pn e to the power of phi bi by phi t. Again, there is no need to by heart this equation. You can simply use understanding, like Pp is a majority carrier concentration. If I am writing of Pp, then definitely it will be higher than the minority carrier concentration. So, Pn into positive exponent. For example, if I am writing Pn, then with respect to Pp, this Pn is minority carrier concentration, and hence we need to use negative exponent of phi bi by phi t. By using same understanding, you can form a relation between Nn and Np. So, I can write Nn is equals to Np e to the power of positive exponent phi bi by phi t. Similarly, Np is equals to Nn of negative exponent. This is called junction law. Now, following this built-in potential understanding, we can find out what is the electric field exists in the depletion region. So, if we see carefully that the depletion region charge across the P and N side can be given by a negative ions at P side and a positive immobile ions at the N side. So, you can see like this, if this is P, this is N, there will be a depletion region formed. This carries a positive charge and this carries a negative charge. Again, here we are assuming the depletion approximation means that the charges are only immobile and there are no holes and electrons available into the depletion region. So, this is nothing but a charge density profile along X. This charge density give you the total charge present into this N side, which is nothing but Q into Nd into D1 into the area. If I make a clear picture of PN junction, so this is your PN junction in a 3D. Right. So, here we are talking about this depletion region thickness, which is D1 in N side and D2 in P side. So, the total charge in this strip is nothing but Q into Nd into A into D1. So, this is the charge available in N side of the depletion region, and the charge available in the P side of the depletion region is minus of Q into Na, because these are negative charge and this is positive charge, minus Q into Na into area into this D2. And as I said that the charge should be balanced and hence there is no net current. So, the charge should be balanced, meaning what? You will get minus Q into Na minus Q into Na into A into D2 is equals to Q into Nd into A into D1. This is mod, which will give you the idea of Na into D2 is equals to Nd into D1. Now, how can I calculate the electric field? You can simply follow the Poisson equation and calculate the electric field. Without doing that, we can simply use Gauss's law and find out the area of this charge density curve. So, electric field is nothing but rho by epsilon s, where if I calculate the area of this, right, then it will give me the total charge. So, electric field can be given as Q into Nd into D1 divided by epsilon s. where epsilon S is the permittivity of silicon, epsilon S into epsilon naught, right. This is the electric field at N side. Similarly, Q times of Na into d2 divided by epsilon S, the electric field at P side of so we can find out the maximum or peak electric field which exists at the metallurgical junction. So it doesn't matter what is the height of N side or P side, the maximum electric field will exist at the metallurgical junction. Similarly, by finding the area of this triangle or the electric field, we can get the potential, which is nothing but, if I am interested in potential, is nothing but the area of this triangle, meaning half of E peak into this complete length will give me what? Total potential. So d1 plus d2. So let us call d1 plus d2 as W. So half E peak into W. If I am interested only in the potential at one region, then I can use d1 or d2 instead of W. So likewise, we can get psi or phi bi is equals to half into electric field of P Q into Nd into d1 divided by epsilon S into d1. So ultimately we will get a quadratic equation. So ultimately we will get a power law, square law equation, Q into Nd into d1 square divided by epsilon S. This is the potential at N side. And similarly, the potential at P side can be calculated as half of Q into Na into d square by epsilon S. If we add it up, we will get the total potential, which is in terms of W. So here you can find out the W as square root of 2 into epsilon S into phi bi by Q 1 over Na plus 1 over Nd. This is clear that the expansion of the depletion region is inversely proportional to the doping, meaning if the doping is larger, the expansion of the depletion region will be lesser at that site. After this, let us consider what will happen if a forward voltage will be applied in the PN junction. So if we applied a forward voltage, meaning the positive terminal of the battery is connected at the P side and negative terminal of the battery is connected at the N side. By connecting this, so you have a P region, you have an N region, and you are connecting a positive and negative like this. By connecting this, the external electric field will be in this direction, whereas the internal electric field or the built-in field will be in this direction. So this is positive, this is negative, and the internal electric field will be this, or I can write EBI. So the overall electric field will be reduced to EBI minus E, and hence the potential barrier height get reduced. So this P side will repel the hole in this side, and this N side or the negative terminal of the battery will repel the electron in this side, and hence you will get a huge amount of carriers flows across the junction, which give rise to a current. We can simply understand this analysis by band diagram. I think it is here. Like, let me plot a band diagram of P and N side. So earlier we have seen that this is a potential height, which is Q times of phi bi, and like this, right? And here the Fermi level exists, EF P, this is EC, this is EV. Now here the Fermi level exists like this. In the zero bias case, the Fermi levels are aligned. But now what will happen when you are applying a positive voltage at the P side and negative voltage at the N side? Remember, when the voltage is negative, the energy will be higher. So this Fermi level gets shifted to the new position. So this is a new position. Let me change the color of my pen. So this is a new position of Fermi level, which is EFN. And by what amount this Fermi level gets shifted? By the voltage what you have applied. Now here you have a conduction band and here you have a valence band. If you now see the potential barrier height is reduced. Earlier the potential barrier height was Q into phi bi, but the new barrier height is Q into phi bi minus V. This gives rise the current to flow across the p-n junction. What happens is, when the barrier height is got reduced, huge amount of electron will diffuse at this side and the holes will diffuse at this side, and hence the current starts to flow in p-n junction. Similarly, here in p-n junction also you can find out the current equation by opting this junction law, which we have already discussed, that when we know the voltage across two different regions and I need to calculate the doping of the other region by knowing the doping of one side, then I can use a junction law. Now whenever you are applying a voltage V, then what will happen? There is an excess charge carriers generated into the p-n junction, and hence because of that, across the depletion region these holes will diffuse like this, and ultimately it will be excess carriers. So here at this side, this is what Pn and this is what Pn. Again, to differentiate this, we are adding Pn0, meaning the whole concentration at n side under equilibrium value is this. But now when you are applying the voltage V, because of the voltage applied V, there is an excess carriers generated, which gives rise to the current, and this excess carrier is nothing but the whole concentration at n side. Now I want to relate the relation between this, so I can simply write Pn is equals to Pn0. Again, this excess carriers are generated because of the voltage, so I need to use positive exponent by phi t. Similarly, if I want to write the equation for n side, so n at p in comparison to the equilibrium value np naught, I can simply write np is equals to np naught e to the power of q v by kt or v by phi t. So these are the equations what we are going to use when we derive the diode current equations. So in this lecture we are not going to derive the diode current equation, but let me tell you few of the approximation which we need to take care. First is, we are assuming depletion approximation. It means there is no mobile charge carriers available into the depletion region, right? So we are only assuming that the depletion region is comprises of immobile ions. Second, we are considering that the excess carriers under steady state will be zero. By using such equations, we need to solve the continuity equation to find out the diode current equation. In addition, we need to use a low level injection. The low level injection says the excess carrier generated into the semiconductor should be less than approximately 10 times of majority carriers. So we are not going too deep in detail, but by solving all such equation, ultimately you will ended up with a diode current equation of I equals to I naught e to the power of V by Vt minus 1, where V is the applied voltage, Vt or phi t is the thermal voltage, I naught is the reverse saturation current, which is nothing but I naught is equals to Q into dP into Pn0 divided by Lp plus Q into dN into Np0 divided by Ln into A. Here Pn0 is the whole concentration at n side under equilibrium. This is the diffusion constant of the hole. This is the diffusion constant of the electrons. This is the electron concentration at p side under equilibrium, and these are the diffusion lengths of hole and electron. By considering all such, we can conclude that when the diode or device or the p-n junction is in forward bias, then there will be a current, and that current follows an exponential law. This equation holds good even for reverse bias. We will see in next lecture. So the circuit symbol of diode is given by this, which simply says that it allows the current in one direction but not allows the current in other direction. This property is called rectification. Here we are applying a voltage V and it gives rise to a current in one direction. Let me conclude with this diode current equation as I equals to I naught e to the power of V by phi t minus 1. We have taken many approximation to simplify this diode current equation, like I mentioned the depletion approximation, low field injection, no mobile carriers here available in the depletion region and all. But in practice these approximations does not hold good, and hence we need to use a non-ideality factor which we called as eta. So V by eta into phi t minus 1. This captures the non-ideality of p-n junction. For silicon, eta is equals to 2. Lastly, if you see this graph which shows the current density, where this point shows the whole current density at this junction. Now the whole will come here and ultimately it will diffuse. So this is Pn0. Similarly, these are the electron current density and it will diffuse. But in the p-n junction there is no diffusion current only. There are some drift component. How can we calculate? So this is the component of drift. So this is whole drift. Similarly, this is drift, right? And hence the sum of these total currents is, and hence the total current is nothing but the sum of drift component and the diffusion component. Here you also can see our assumption does not hold good that no mobile carriers are available in the depletion region, because there are some carriers in the depletion region which supports the current into the depletion region and maintain a current continuity. So let me summarize this lecture. In this lecture we have seen the p-n junction, which is a fundamental semiconductor device. We found that when two different materials are joined together, then a p-n junction forms. We analyze the p-n junction roughly in an zero bias condition, and we also saw that how p-n junction behaves when a forward voltage is applied. P side of the junction is connected to the positive terminal and n side of the junction is connected to the negative terminal. So we'll stop here for today. Until then, take care.